Hi, in last couple of videos we were dealing with second order difference equations. We already know how to solve them, we know how they work, and we already applied them to two different economic models. So the next step is to bring this a little bit closer to reality and moving towards time series analysis. And as usual, we're gonna do a simple model of GDP, this time of course using second order difference equation. Okay, so this is where we start. Look, imagine that we have data on GDP, which is given by YT, and we have this data on GDP in many periods. So what we could do in such circumstance is to estimate econometrically this equation. Let's just say that we are going to skip the problem of proper tools to estimate this equation, but let's just say that we did. And look, it's not that problematic, right? What we can see over here is that we've got simply GDP at time t, a constant, and we regress this GDP at time t on a constant, two lags of GDP, and we are assuming that there is some deterministic trend, which is simply captured by this expression plus beta t, and plus beta 1t. Okay, of course, assuming that we are going to, now if we were estimating this model, right, we would get specific values of these parameters. However, of course, because we are not estimating it right now, let's assume a little bit, and as you will see that if you would estimate an equation like that, that would be exactly the coefficients you would get. However, I will make one specific assumption that goes a little bit beyond it. Okay, so what do we have over here? First, constant must be positive and it must be bigger than beta 1. And look, because this is a GDP, this is a coefficient, you might expect that this expression is somehow related to initial level of GDP. Of course, all of them are. However, we expect this alpha 1 to be very, very big, because this will give us our initial point. Okay, then we impose two restrictions on the coefficients a1 and a2. We are assuming that a1 needs to be somewhere between -1 and 1, and a2 needs to be between 0 and 1. And look, this might not seem that important, but you will see that later that it is. Those two assumptions are showing us that a1 plus a2 is always bigger than -1. Again, this will come handy a little bit later. Okay, so what should we do next? Well, probably we should start by rewriting this equation into a form that we are familiar and we know how to deal with. So we're going to put all the expressions with y on the left hand side, everything else is going to stay on the right hand side. So look what we are getting. We are getting that yt plus a1 yt minus 1 plus a2 yt minus 2 equals to alpha 1 plus beta 1t. Okay, look, this again is where we start, because this is a econometric model that we can actually estimate. However, we don't like the fact that here we have t minus 1, t minus 2, but of course we can always move the subscripts. So we get the equation that we know and like very much. T plus 1 plus a 2y t equals alpha 1 plus beta 1 t. Of course, those equations are equivalent. And now that we've got equation in a form that is very familiar to us, what should we do next is to find complementary function. Okay, so right off the bat, when talking about complementary function, we should distinguish which of the three cases we have: distinct roots, repeated roots, or complex roots. However, in this case, as we've got in the assumption that a1 squared is lower than 4a2, by assumption, this implies that, of course, we've got a case number 3, which is complex roots. Okay, now, we of course know that in case of complex roots, the complementary function assumes the following form. A5, this is 5, or cosine t plus a6 sine theta t. Okay, and of course, what is important for us in here is r, right? Because what do we know? Just from the assumption, we know that we will have fluctuations, right? The only question remains is whether those fluctuations are going to be dying down or increasing in their magnitude, right? So, of course, we need to calculate r. This just gives us, the fluctuations, and of course, r, t, is something that scales the fluctuations. However, we know that r is simply equal to square root of a2. And we also know that a2, by assumption, is between 0 and 1. So look, if I substitute it over here, I'm going to get that this is a2 to the power of t, a5 cosine theta t plus a6 sine theta t. And, just to make this look nicer, let's write it in a little bit different way as a2 to the power t over 2. Okay, at this moment, because a2 is between 0 and 1, we know that this expression with time is going to get smaller and smaller and smaller and smaller. So we know that on one hand, we've got fluctuations, and those fluctuations, of course, come from here. Look, we do not calculate thetas. Why? We are not that interested at this moment in a specific form of this expression. All we know, and all we want to know, is that it generates fluctuations. And of course, now that we know that a2 is between 0 and 1, right, we also know we will have convergence. Okay, so now we dealt with complementary function, of course, the next logical conclusion, the next logical step here is to tackle a particular solution. Okay, give me a second. Okay, so of course, in order to find particular solution, we will use method of undetermined coefficients. Look, we were dealing with very similar case before, actually twice, so now we just need to use exactly the same trick. We see that here we have just polynomial of the degree 2, which has of the degree 2, which has coefficient and a constant, right? So what we need to do over here is to simply assume that a particular solution will take this form, right? So we will assume that yt is given by b0 plus b1 t, right? And now look, where does it lead us? Then yt plus 1 is equal to b0 plus b1 t plus 1, which gives us b0 plus b1 plus b1 t, right? And by the same token, yt plus 2 is equal to b0 plus b1 times t plus 2, which is equal to b0 plus 2 b1 plus b1 t. Okay, now that we've got this down, the next thing to do is to take our proposition and substitute them into the equation. Okay, and what do we get over from there? So we start with having b0 plus 2b1 plus b1t. It doesn't need to be in parentheses. I want you to see step by step where everything is going. Then we have a1, right, times yt plus 1. So now we have b0 plus b1 plus b1 t. Okay, and then we have plus a2 times b0 plus b1 t, and this is equal to alpha 1 plus beta 1 t. Okay, now what should we do next? Look, definitely we need to organize those expressions somehow. But what is the key? Look, of course, key here is pretty simple. We want to have expressions with t together, and we want to have constants together. So probably we need to calculate some of this stuff out. The first part stays the same. And let's start by collecting constants. Here we will have a constant, here we will have constant, here we will have two constants, right? We will have b0 to b1 plus a1 b0 plus a1 b0 plus b1, right? From this, and finally we will have plus a2 b0. You know what? Let's already divide this also to two parts. a1b. Okay, and this will be a constant. We will simplify it a little bit in a second, but still our constant, right? Alpha 1. So, what do we need to add here? We need to now add all the expressions with t. So we've got b1, then we've got a1, b1, and we've got a2, b1. Okay, and this is equal to alpha 1 plus beta 1t. Okay, what more can we do? Well, the nice trick to deal with this expression is to divide those expressions into the ones that are associated with b0. So look, we've got this one, and this one, and this one. So I can simply write that. I can simply write that as we've got 1 plus a1 plus a2 b0, right? 1, 2, 3. And then we've got 2b1 plus a1 b1. So we will have here plus 2 plus a1 b1. Okay, and then of course we can simplify this further because we will have b1 1 plus a1 plus a2t. And we've got that this is equal to alpha 1 plus beta 1t. And look, now we can clearly see that over here we've got similar expressions, and over here we also have similar expressions. So what should we do? We need to now calculate how much is beta 1 and how much is alpha 1. So we've got that beta 1 is equal to b1 1 plus a1 plus a2, right? Because those two need to be the same. So if we get out of this that b1 is equal to beta 1 over 1 plus a1 plus a2. However, there is an issue here. What if a1 and a2 together are equal to -1? We're not gonna have a solution. But wait, we assumed that a1 plus that a1 is between -1 and 1, a2 is between 0 and 1, so the sum of the two must always be bigger than -1. So this solution definitely works. Okay, and now we need to do the same. We need to do exactly the same thing for the constant, and we already have some information that we can use it in there. So we've got now that. Okay, so we have that 1 plus alpha 1 plus alpha 2 b0 plus 2 plus a1 b1 is equal to alpha 1. Right? First thing we should do over here is to move this expression to the other hand side. But look, now we know how much is b1. b1 is beta 1 over 1 plus a1 plus a2. Or simply put, right? So if we want to know what is B0, we divide both sides by this, and we finally get that B0 is alpha over 1 plus A1 plus A2 minus this. Okay, and look, we finally arrived at what we wanted. So, what did we get is that, assuming this is the equation we had to begin with, if we estimate this equation, we will be able to get the parameters of the GDP time path. Now, what is this GDP time path? Well, it goes like this. GDP at time t is equal to. Okay, we need to, of course, start with the complementary function. So, we had that this is a2 to the power t over 2, right? Times a5 cosine theta t plus a6 sine theta t. Right? This is the first part. Now, the second part, of course, is particular solution. Now, this particular solution we got over here. First, we need to have a constant, and this constant is alpha 1 over 1 plus a1 plus a2 minus beta 1 2 plus a2 over 1 plus a1 plus a2 squared. Okay, and finally, we add to it beta 1 over 1 plus a1 plus a2 times, of course, time t. Okay, so the expression that you can see over here is the time path of GDP. What do we know about it? Look, basically, if we are assuming that we've estimated all these 4 parameters, right? We've got 4 parameters here. We've got A1, A2, and alpha 1 and beta 1, right? Now look, if we know all of them, we can simply plug them in, A2 over here, right? And everything else over here to get the solution. And look, this is very important because knowing that we got this specific particular solution gives us appropriate tools to discuss properties of GDP and what will happen if GDP is thrown out of the equilibrium by some shock. So the next thing we are going to do is going to be drawing this picture and making some inferences about GDP. To make the exposition a little bit easier, let's use some colors and introduce some shortcuts. So, for example, let's just say that this entire coefficient that we have estimated econometrically, we're just going to call alpha without any subscript. Okay? Now, the coefficient that we've got on t over here, we're just going to call beta, right? This makes is definitely the equation looks a little bit better and more digestible, I would say, because it turns into yt equals to a to t over 2 and 5 cosine theta t plus a6 sine theta t plus alpha plus beta t. Right? Okay, so in this case, let's start drawing. Okay, so on this graph, here we will have GDP at time t, and here we will have time. Okay, so let's start with our alpha. Alpha, we've got over here. And look, based on what we know, you can make a case that alpha can either be negative, right? Assuming that first expression is smaller than the second expression in alpha, right? So, however, we need to remember that we are assuming that beta 1 is a coefficient that can be 0.7 or 1.3. However, alpha is going to be a number in GDP terms. So it can be 10 billion, right? So again, right off the bat, we can exclude this possibility. And then, look what happens. At time 0, right? Everything here is 0, 0, and this disappears, right? At time 0. So we start at time 0 from some level alpha, right? And what happens then? Look, then we know that GDP increases by beta every year, right? This is a simple linear function. Okay, that is not the most beautiful alpha. Let's make it nicer. Okay. This is a simple linear function, so it will look like this. Right? This is GDP trend within this structure, and it's represented by a straight line. However, we should remember that we are in the domain of difference equation. No, differential equation. So we are assuming the time is discrete. So look, what this means is that assuming the GDP is in equilibrium, so we are following this. Of course, we will be on that line, but we will be on that line at given time periods, right? So the intervals should be identical, but of course, it's really hard to draw. So let's assume that GDP is constantly in the equilibrium. Then, right, we would be on some point over here that on some point over here, right? And this is what we would see, right? Okay, so now let's make a scenario. Let's just say that for first 4 periods, GDP is in equilibrium and it grows so it grows at rate beta, right? So then something happens in period number 5. And look, what happens is that we've got some negative adverse shock to the economy. And because we've got this adverse shock, GDP is now below its trend value. However, we know how this particular economy works, right? How it adjusts to equilibrium. Because we know that this adjustment process is again described by complementary function. And we know its properties. We know about that we've already established convergence. And we know that this path will be characterized by fluctuations. So, how should we draw that? Look, again, let's start by drawing it, this part, without restraining ourselves only to a discrete domain. So let's move within continuous domain. So what we would expect? We would expect that definitely GDP is going to go back to trend. However, it will overshoot it and then it will again go below trend and then it will move even closer to it. Okay. However, again, remember, we're not going to see that in data. What we're going to see in data? In data, we're going to see that point. In data, we're going to see that point, 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 and that point, right? So, if you would plot this on a graph, you would not see a beautiful converging trigonometric function. Instead, you would see those points. But the rules that govern this process still follow the principles, the same principles. However, we just see the realizations only at some certain time moment. Okay, this is everything. We're not gonna demand anything more from you for this class. So thank you, and I wanna wish you all a good luck on the final exam. Take care.